Part 1, Understanding Energy Efficiency in the NCC. So what we'll learn, we're going to look at what energy efficiency means and explore some of the current definitions. We're going to look at why energy efficiency is important. We'll take a look at key energy efficiency concepts and terminology. We'll look at how to achieve energy efficiency. We'll look at energy efficiency requires in the NCC and other resources. Before we get started, it's actually really important to note that the NCC does not contain a definition of energy efficiency. And if you think back to what we've been discussing in the previous two presentations and this notion of italicized definitions that was within both two volumes. And this is because there isn't an exact agreed definition for energy efficiency. The most technical definition and the source of the term relates to how much output a machine or energy service gets for the energy that it's input. So how much of the energy input to a machine is lost and how much is able to be used to produce an output. The term is used much more broadly now in the context of reducing energy use or conserving energy. So in building terms, and you're probably across this, but key sources of energy use are heating and cooling in the living spaces, lighting, heating hot water, and operating electronic devices. The NCC energy efficiency provisions are designed to ensure that a building is designed and constructed in such a way that it's possible to operate the building with an appropriate minimum level of energy use. And this is also in relation to its purpose and its geographical location. So there are performance requirements for both class 2 to 9 buildings, which are kind of commercial buildings, and class 1 to 10 buildings, which sit in domestic. And the specific performance required depends on factors such as the location, as we noted. To give some context to this, let's go through how some other organisations provide context to the term energy efficiency. So I've got 4 definitions from various sources, each is cited, so you actually can go and look up the context in which these sit. The first, energy efficiency is the use of less energy to perform the same task or produce the same result. I'll let you go through these other definitions in your own time, but it's worth just gaining an understanding of where we're kind of sitting in all of this. So why is energy efficiency important? Look, I know a lot of you are across this from your studies at uni and your time in practice, but let's look at why it's really important. So in recent years, awareness has increased about increasing levels of greenhouse gas or GHG emissions and the effect that these emissions may have on global warming. While greenhouse gases are a natural part of the Earth's atmosphere to capture the sun's warmth, greatly increasing the amount of greenhouse gases in the atmosphere is increasing the natural capture of heat, resulting in the warming of the planet that we're all seeing. While the building sector is not the largest contributor to greenhouse gas emissions, it's one of the fastest growing sources. Energy used in building accounts for around 20% of all of the energy-related greenhouse gas emissions in Australia. The NCC aims to contribute to reducing greenhouse gases by increasing the energy efficiency of Australia's building stock. Energy efficiency reduces pressure on bills in the short term because households and businesses pay less for electricity while the equipment maintains the same level of service. For example, if you think about it, efficient fridges can have the same features and storage capacity as minimum standard fridges, but they'll cost a lot less to run. Energy efficiency also reduces pressures on prices in the future because it reduces the need to expand the electricity supply system to cope with increasing demand. This means that all energy users can benefit from energy efficiency actions. So the Australian Energy Market Operator, AEMO, lists increased adoption of energy efficiency measures as one of the factors in the recent reduction of energy demand. And all of this information came from an energy efficiency action plan that was prepared by the government, and I've included the link on the slide for you. Let's go through some key energy efficiency concepts. Now, you may already have an understanding of the terms on the slide, but again, these definitions of the terms are specific to the NCC. So it's important to make sure you go back and check the definition and make sure you understand it. Don't rely on your everyday understanding of these terms. Some energy efficiency terms are defined differently for Volume 1 compared to Volume 2. So, for example, the definitions of conditioned space, building envelope and glazing, and you might want to note that down. So let's look at climate zones. The map is figure 2 from schedule 1 definitions that sits in any volume of the NCC. The map, together with its associated table, defines the 8 NCC climate zones for energy efficiency. There is a larger expandable version of this climate zone map available at the ABCB website, along with state and territory maps. The climate zones are shown by the different colours. So climate zone 1 you can see is a dark orange colour that sits in northern Australia, and then climate zone 8 is the white parts of the southeast of the country. The 8 NCC climate zones are described as climate zone 1, which is high humidity in summer and a warm winter, climate zone 2, which is warm humid summer, mild winter, climate zone 3, which is a hot dry summer and a warm winter, climate zone 4, hot dry summer, cool winter, climate zone 5, warm temperate, climate zone 6, mild temperate, climate zone 7, which is a cool temperate, and then our climate zone 8, alpine. So appropriate design for the climate is key to achieving energy efficiency in a building. For example, in climate zone 1, buildings should be designed to reduce heat gain from the sun. So you want to minimise the amount of sun which enters windows and how much heat the windows will transmit in and out of your building. Ventilation is also obviously very important for cooling the building naturally. So in climate zone 4, which was hot dry summer and a cool winter, you want to minimise the sun in summer and ensure adequate ventilation. But in winter when it's cooler, you usually want to maximise the amount of sun you get into the building to make sure that you're warming it naturally. In climate zone 8, where it tends to be cooler all year and very cold in winter, your aim is to minimise the loss of warmth from inside the building. Let's jump to the next one. So conditioned versus non-conditioned spaces. Before we start looking at these, please note that the explanation for conditioned space on this screen is simplified a little for the context of the presentation. And this is because the purpose of the presentation is not to present you a detailed technical analysis of energy efficiency requirements. Write this down. The definition varies between volume 1 and volume 2. So please make sure you take a look at the definition in the relevant volumes before you make any decisions based on the classification of a space as conditioned or non-conditioned. Again, the NCC doesn't define non-conditioned space, but it's logically the opposite of a conditioned space. Since the definition of conditioned space varies a little between the volumes, so does what would be considered a non-conditioned space. So again, make sure you check before you make any assumptions. This classification is really important because a non-conditioned space will impact on the temperature in an adjacent conditioned space. So if there's a temperature difference between them. So for example, a warm conditioned space that has no conditioned spaces on 3 sides will lose heat to all 3 of those non-conditioned spaces. If a cool conditioned space has a warm non-conditioned space on one side, so for example, the western outside of a building in summer, then the conditioned space will gain heat from the non-conditioned spaces. This heat loss and gain continues between any spaces or surfaces with different temperatures, essentially until the last 2 spaces or surfaces have the same temperature. Let's take a look at building fabric and envelope. The building envelope can be thought of as identifying the boundary between a conditioned space and a non-conditioned space. So while the building envelope is always formed from parts of the building fabric, some parts of the building fabric may not be part of the building envelope. So for example, internal walls which separate conditioned spaces, i.e. rooms, from each other. The materials used in the building fabric and the design, construction and integrity of the building envelope help to make the building more energy efficient. They can help to reduce the transfer of heat into and out of the building. So this helps to maintain a comfortable temperature in the conditioned spaces and reduces the need to use energy to heat and or cool the building. Using appropriate materials in the building fabric along with appropriate insulation can help to limit unwanted heat flow and reduce the amount of energy needed to heat or cool the conditioned spaces in the building. If you identify the areas of the building that are conditioned or can be conditioned, or for volume 1, constitute a habitable room, which is also defined as part of volume 1, which is likely to be conditioned if it becomes uncomfortable, then the building envelope is made up of the walls, roof, ceilings and floors that form the boundary of these conditioned spaces if there's a non-conditioned space on the other side. Thermal mass, you're probably all across this one. Thermal mass is a term used to describe how well a building material stores heat. So materials that have a high thermal mass absorb heat from the environment and then release that heat slowly when the surrounding ambient temperature goes down. Thermal mass exposed to winter sun warms during the day, and it will warm the space it's in as it cools. So as the thermal mass kind of cools down overnight in summer, it will cool the space as it heats during the day. So effective use of thermal mass combined with good solar orientation can greatly reduce the need for mechanical heating and cooling, which is what we want. Ventilation. So ventilation, as you probably know, refers to the natural movement of air in or out of a building through an opening designed exactly for that purpose. So it could be a permanent opening such as a vent. It may be part of a window that can open in the wall or in the roof, or it could be a door or other device that can be held open. Good ventilation can help to cool a building naturally without the use of artificial means or energy. Now, heating and cooling loads. As you may know, a building's heating and cooling loads are calculated using approved software. These calculations are based on the building's size, design, climate zone, orientation, ventilation, and the materials used in the building envelope, along with a few other factors such as shading from other buildings or significant trees, and even the colours used in external material. Only approved software can be used to calculate heating and cooling loads, and this software is different for residential buildings versus commercial buildings, and even to some extent between the different states and territories. A building's heating and cooling loads are the key factors that determine a building's star rating under the various energy efficiency rating scheme. Only NAITH's software allocates a star rating to buildings. Software approves for use in H6V2, which is verification using a reference building, is unlikely to allocate a star rating. The classification of conditioned space in a building makes a difference to the calculation of heating and cooling loads, and therefore the building's energy efficiency star rating. Acceptable heating and cooling loads for buildings are different in different climate zones. So this is an acknowledgement that it's easier to minimise energy use for heating and cooling in some climates than in others, particularly the more extreme climates. For example, it would be really difficult to design a building that had no requirement at all for mechanical heating in an alpine area. To require a building in climate zone 8 to have the same heating and cooling load as a similar sized building in climate zone 1 or 4 just wouldn't be reasonable. So heating and cooling loads and the software used to determine them will be discussed in a bit more detail later in the presentation. So now we're going to take a look at some key terms relating to energy efficiency of glazing and window systems. These terms are used frequently in the parts of the NCC that discuss energy efficiency requirements, and it's difficult to understand those parts without understanding these concepts. So let's look at glazing. In the NCC, the term glazing includes the glass and the frame associated with it within the building envelope. So the term is defined slightly differently between volume 1 and 2, so again it's best to look these up. It can apply to windows and doors in walls and some roof windows or skylights. It's important to note that the glazing energy efficiency requirements in the NCC apply to windows in the building envelope only. So a window in an internal wall does not have to meet these performance requirements. For example, a window placed high on the wall between a hallway and study to let in more light. So note that this window might have to meet other performance requirements, i.e. to ensure safety or to minimise noise disturbance. R value or total R value. R value is a measure of how well a material or building element insulates. So that is how well it resists the transfer of heat from one side to the other. It's a measure of the material's thermal resistance. R value is a defined term in the NCC, and the formal definition is the thermal resistance of a component calculated by dividing its thickness by its thermal conductivity. The higher the R value, the better the material is at insulating, so that is, the less easily it will transmit heat. The NCC also defines the total R value of a building component or assembly. This is a calculation of the sum of the R values of the individual component layers in a composite material or assembly. So think of like a wall build-up. The calculation includes any building material, insulating material, air spaces between the different layers, and associated surface resistances. So if you think of the pre-made exterior insulation and finished wall panel, which could be assembled for 4 or 5 different layers. For example, a metal outer layer, a foil moisture lining, an internal frame, an insulation layer, and an inner shell. Each of these layers will provide some degree of thermal resistance. So the total R value is the sum of all of these, plus the thermal resistance of any air gaps. Builders might not often have to calculate an R value, as these values are usually included in product specifications. And you'll usually see R values quoted for the building materials typically used in walls, floors, ceilings, and roofs. You might need to check whether the value quoted in the total R value or just the R value for that element. So you might need to also calculate an R value if you're using an unusual building material or method. For the purposes of calculating heating and cooling loads, and therefore energy efficiency star ratings, it's generally the total R value of a wall, roof, ceiling, or floor build-up that matters. Let's look at U value, or total system U value. So U value is a measure of how easily a material or building element transmits heat from one side to the other. So it's a measure of the material's thermal conductance. The higher the U value, the more easily the heat is transmitted through the material. The lower the U value, the better the material is at resisting the transfer of heat, so that is, it insulates better. A material's U value is the inverse of its R value. U values are calculated for any type of windows, including those in walls and roofs and ceilings. The NCC defines the total system U value of a building component or assembly, and this is a calculation of the sum of the U values of the individual component layers in a composite material or assembly. The calculation includes any glazing, the frame, any insulating material in the frame, thermal breaks or air spaces between the inside and the outside, and any gases used, so for example, argon that sits between double glazed windows. The definition of total system U value varies slightly between NCC volumes 1 and 2. You're probably starting to see a theme here. And you'll usually see U values quoted for glazing and window systems. You need to understand whether the value quoted is the value of the glass or frame or a total U value for the entire window system. Solar heat gain coefficient. In terms of insulating properties and energy efficiency, a high R value is usually good, but whether you want a low or high solar heat gain coefficient and U value depends on how you want the particular window to function. So in a northern location where you want to keep the sun out of the building all year round, a window system with a low solar heat gain coefficient and low U value would be preferred. But if we flip this, in a southern location where you might want to allow the sun into the building in winter but exclude it in summer, a high solar heat gain coefficient and a moderate U value might work better. The solar heat gain coefficient and total SHGC, I'm going to swap to the acronym now to save us all time, are defined terms in the NCC. So the SHGC is a measure of the proportion of solar energy or radiation that passes through a glazing system. And again, make sure you realise that the glazing system includes the glass and the frame. So in other words, it measures the solar heat gained through the glazing system, and it's a measure of the glazing's solar transmittance. So this is expressed through as a number through 0 to 1. And a high solar heat gain coefficient means that the glazing system allows more solar energy or heat into the room. So i.e. if the value sits closer to 1. So a low solar heat gain coefficient means that the glazing system allows less solar energy or heat in a room. So then the value would be sitting closer to 0. A low solar heat gain coefficient is good in some circumstances and a higher one is better in others. So this really depends again on how you want your glazing to perform and function within the building. The definition of total solar heat gain coefficient varies slightly between the two volumes. Like the U value, you'll usually see solar heat gain coefficients values quoted for glazing and window systems, and you really need to understand whether the value quoted is the value of the glass or the frame, or again for the entire window system. So how do we achieve energy efficiency? Optimal orientation is key. So a building that's well positioned on the block to catch winter sunshine or reduce summer sunshine, for example, in southern latitudes, will be much more comfortable to live in than ones that's poorly positioned and will need far less mechanical heating and cooling. This is one of the simplest and most effective ways of obtaining good energy efficiency, although it's not enough on its own. The materials used in the building fabric also play a role, so in warmer climates, lightweight materials that reduce thermal mass can be effective. However, in cooler climates, materials that have more thermal mass are usually preferred. Glazing that's appropriate to the climate is also important, considering the orientation and position as well. This involves considering more than just the type of glass and frame. It extends to the size of the glazing or the windows in these different walls. In southern latitudes, large windows on the north that get winter sun can help to warm the building during the day and at night if there's a sufficient thermal mass in the house. In the same situation, windows on the southern side of the building should ideally be kept smaller, as they're acting as a source of heat loss regardless of the type of window used. And that also includes its glazing in the system. Insulation is also key to reduce loss of heat in cooler weather and heat gain in warmer weather. Insulation can be in the ceiling, under the roof, under at the sides of the floors, and in the walls. So in other words, it sits throughout the building envelope. Ventilation is another key consideration that's often forgotten. So for example, in warmer climates and in summer in most parts of Australia, good ventilation can help clear the heat that builds up during the day and provide a comfortable temperature for sleeping at night. In climate zones that are warm all year round, i.e. climate zone 1 and 2, good ventilation can make a big difference to how much heat builds up inside the building and to the user's perception of the thermal comfort within that building. Shading can also be useful to consider. For example, in cooler climates, positioning the building to avoid overshadowing. Energy efficiency building systems and appliances also play a key role. So a more efficient heating system can significantly save on the energy required to heat a building when mechanical heating is required, that is. So the key mechanical systems that contribute to energy use are heating and cooling, lighting, heating hot water, and pumps and other equipment relating to pools and spas. It's important to note that small appliances are also big users of energy, particularly as the number and size of devices in a typical home or workplace continues to increase, and as they tend to use more and more standby power. But as they can vary, i.e. they're not a permanent fixture within the building, they're not actually included in assessment of energy efficiency for the purposes of building approval. However, all efforts to minimise heat loss and gain are potentially wasted if the building isn't well sealed, since all the warmth inside the building in winter will escape and unwanted heat will enter the building during summer. Good building sealing means that if you use energy to heat your building, the warmth will be retained for longer inside the building, and so the building won't require as much mechanical heating. Ditto in relation to cooling the building. So all of these factors listed and others have to be considered at the design stage when it's cheaper and faster to ensure that the building will function well for the climate zone. A building is approved to be built as designed, which includes all of the energy efficiency features in the approved plans. This then must be carried through in construction. So for example, the building must be built as approved, and you shouldn't be changing features that contribute to the energy efficiency of the building. So for example, reducing the insulation in walls, installing ceiling insulation poorly, or choosing a different material for walls or glazing, given these can greatly change the actual energy efficiency in the building. Energy efficiency in the NCC. Building energy efficiency is largely assessed by rating likely performance of the building, as designed, against the standard. A building can demonstrate compliance with the majority of the NCC energy efficiency performance requirements by getting a rating against the nominated energy efficiency standard. So some performance requirements require other forms of assessment or evidence. The standards that can be used to rate buildings are different for commercial and non-commercial or domestic buildings. There are also some differences between the standards that are acceptable in different states or territories. Both Volume 1 and 2 contain performance requirements that focus on the performance of the building fabric, which means the extent to which the building fabric allows for heat flows in and out of the building. The energy efficiency of the key fixed building services such as air conditioning systems, lighting and hot water generation. Volume 1 also includes requirements for the energy efficiency of swimming pool or spa plant and provision to allow for monitoring of energy use. Volume 2 includes requirements for understanding adequate sealing of the building envelope, and these inclusions reflect the key concepts and approaches discussed earlier in the module as making a difference to building energy efficiency. Some of the provisions in Volume 3 also relate to energy efficiency. So in particular, the performance requirements for heated water services require consideration of the amount of energy used to heat the water and the greenhouse gas emissions that are released. Other resources? The ABCB has developed a range of calculators to assist architects to develop energy efficient building solutions. I've given you the link there just under that first dot point. The use of these calculators may be helpful, but it's not mandatory, so you don't have to use them, and they're not compliance tools or verification methods. For example, you can use the ABCB's glazing calculator to identify or test glazing combinations, but you should not use the results of the calculator as the sole evidence that the glazing chosen for a building is appropriate and meets the performance requirements. There are videos on how to use some of these calculators, and there are handbooks specifically on applying the energy efficient provisions of each volumes 1 and 2. There are also a lot of different case studies that cover a wide range of topics. Again, the links are on the slide here, so you can jump in and take a look. Okay, so key points. Energy efficiency provisions in the NCC aim to reduce the energy required to operate a building and therefore the greenhouse gas emissions produced by buildings in Australia. They focus on the building envelope to minimise the use of mechanical heating and cooling to maintain a comfortable temperature within a building. These provisions encourages efficient use of energy to operate a building services, included heating water services, and use of low greenhouse gas energy sources. There are different requirements for buildings in different climate zones and of different building classifications.